Okay, so let's look at the part 2 of the introduction. This is just a little bit about data, and then the part 3 is the lab exercise, the actual lab exercise after part 2. So we talked in the first lecture about the data space story. We talked about what visualization is. We looked at some examples of visualization. We looked at the goals of visualization, presentation analysis, exploration, and acceleration. We discussed information visualization versus scientific visualization, and we discussed the visualization pipeline. Just in case you forgot from the last lecture what we talked about. We're going to talk about data in this lecture, and we're going to talk a little bit about color, mention a little bit about color. So in this class, we have a very data-centric point of view of the world, right? So the data is the center point. Now, that's not true for all data visualization classes, by the way. Some people will start with the person, they have a human-centered pedagogy. But in this particular module, the data is the driving factor for the visualization itself. So whenever we have a data set, we want to ask some targeted questions to help us get started. For example, what is the dimensionality of the data, right? Where does the data come from? Which visualization methods make sense for this kind of data, right? Why did the user collect the data in the first place, right? And what would the user like to learn from the data, right? This is what's happening, right? Everybody's collecting data. Usually, not always, but usually the data is collected for a reason, to answer some special questions. That's not always true, though. Sometimes people are just collecting because they like it. They just think, oh, this is fun, I can do it, I'm just going to collect. And maybe the questions and things come later. Right? So about dimensionality. The word dimensionality is slightly different depending on the context. So in scientific visualization, dimensionality means something slightly different than in information visualization. So in scientific visualization, there's an inherent spatial domain, and we can describe the data as one-dimensional, two-dimensional, three-dimensional, maybe 2.5-dimensional, maybe zero-dimensional. Does anybody know what those terms mean in this case? Does anybody know what one-dimensional data looks like in scientific visualization? Any brave people in the audience? Where's the attendance? So the computer science. You might know the answer. Any ideas? No? So one-dimensional, in the case of scientific visualization, is a line, right? That's one-dimensional. A line is one-dimensional, right?
How you can represent the line one-dimensional?
So, like a lot of data is one-dimensional. So, for example, when you use a bar chart, it's just you presenting a set of numbers, and that's one-dimensional, right?
Actually, because if you want to represent not a line, just a dot, you need two-dimensional.
So that's another question. In 2 dimensions, does anybody know what 2 dimensions corresponds to? X and Y, which corresponds to what? Anybody have any idea? So the 1D is a line. 2 dimensions is a plane. So a line, a plane is like a flat surface. Yeah, that's 2 dimensions. So this screen is 2-dimensional. We say, it's like an x-axis and a y-axis. So we have 1D is a line, 2D is a plane, 3D. Does anybody know what 3D corresponds to?
Probably if we stretch it.
Stretched what?
If we stretch this plane up,
Stretch the plane where? How?
like horizontally and vertically as well.
Like horizontally, meaning this way?
No. If this is 2D, then 3D should be behind it probably.
3D is behind the plane.
Yeah.
Okay, that's right. So if we add depth, that's 3 dimensions. So then in that case we have x, y, and then depth. So a volume, that's 3 dimensions, or 3-dimensional data. Anybody know what 4-dimensional data might look like in this case? When we add, who said that? Nice. Time. When we add time, then it becomes 4-dimensional data. If it's volume data and we add time, so it's changing over time, we have multiple time steps. That's 4-dimensional data. Now, we also use the terms instantaneous or time dependent. So instantaneous means there's just one snapshot. It's independent of time. And time dependent means there's another dimension, the temporal dimension. So it's changing over time. An analogy is a photograph. When you take a selfie, for example, a photograph is an instantaneous 2-dimensional data set. Right? There's no time. But if you hit record, video record, and you have a film, that's actually 2 dimensions plus the time. We could say that's also 3-dimensional data, but it's 2-dimensional time-dependent data. The video, right? Because it's X, Y images, and then time added onto it. Right? So examples include medical data, right? We saw the examples of medical data, the skull and the head. That's 3-dimensional flow visualization, flow simulation. And usually this data represents something that has a physical correspondence, something that happens in the real world, or a physical phenomena, right? Like a person walking, or a river flowing, or a tree growing, something that exists in nature. We also have this term that we use sometimes called 2.5D. Anybody want to guess what that might mean? Any mathematicians? I don't think there are any mathematicians here. That is that corresponds to surfaces in 3D. It's not a strict definition, but a surface in 3D, if a surface is actually infinitely thin, so it doesn't actually take up any volume of the surface itself. However, it requires 3 dimensions to describe it, or to visualize it. So it's sort of like halfway between 2D and 3D. So sometimes we can say 2.5D to describe surfaces in 3D. Now that's dimensionality in the scientific visualization sense, right? In the information visualization sense, it's a little bit different. So there's no inherent spatial reference for information visualization data. This is abstract data, right? And the spatial arrangement is designed for, or derived, right, for the visualization. If you think of a spreadsheet, and we're going to look at spreadsheet data in the lab. If you think of a spreadsheet, maybe you have a spreadsheet of data. For example, maybe you're shopping for a car, right? And you have a spreadsheet that describes a bunch of cars. Maybe you have in the first column the name of the car, the manufacturer in the second column, the year the car was manufactured in the third column, the color of the car on the fourth column, how much the car weighs in the fifth column, how much it costs the dealer in the 6th column, how much it costs you in the 7th column, and the engine size in the 8th column. We would say that each one of those columns is a dimension of the data. So every attribute there is a dimension. So that I just described an 8-dimensional information data set, right? So examples include data usually often stored in databases or text or spreadsheets, survey data, financial data, call center data, and so on, right? So that's all abstract data. So there are different data types, right? So we have scalar data, what we call scalar data, vector data, and multidimensional data. So scalar data is usually described as a number. This is what you usually think of as data, right? Numbers, right? You have natural numbers, integers, rational numbers, real numbers, complex numbers. I guess there are no mathematicians here. Does anybody know what a natural number is?
It starts from 1 goes to.
That's right, the numbers you can count on your fingers. Yep. And integers. Anybody know what integers?
Line of number from minus to.
That's right, the natural numbers plus the negative numbers.
But the natural number is from 0 to 1.
So the natural is 0, 0. Yeah.
So you can include the 0 because it's minimal since the natural number is falls under the 0 and successor.
Okay, good. Rational numbers. That starts to get more complicated. So rational numbers are numbers that can be expressed as a fraction. It's not really that important actually, but yeah, it's just an example. There's irrational numbers, too, numbers that can't be expressed as a fraction, like the square root of 2. Real numbers are floating point numbers, so all the numbers between, for example, 0 and 1, and all the numbers between the integers. And then there are complex numbers, which have 2 components, the real and imaginary parts, but we don't really talk about those. It's not that important. It's just the point is we have numeric data, but we also have vectors and tensors. Those are another sources of data. Anybody know what a vector is?
It has like 2 dimension, and has to be shown like by 2 points.
That's right. A vector can have 2 dimensions. So it describes a direction, and it has a direction and a magnitude. So it can be 2-dimensional or 3-dimensional. Vector could be 3-dimensional space, and then a tensor. A tensor is more complicated. We do have tensor field visualization. We're not going to really talk about it in this short class. But we also have non-numeric data, right? So nominal values like first, second, third, names like Joe, Sally, right? Sally's our favorite name. Text, right? Text is data. This is non-numeric data. Then you have multi-dimensional, multi-attribute data, which is what I described in the spreadsheet of cars, like the columns in a spreadsheet of cars if you're shopping for cars. I'm not shopping for cars, but some people do shop for cars, right? You can imagine a spreadsheet, car type, manufacturer, year of manufacturer, country of origin, the miles per gallon, the horsepower, the number of cylinders, how much it costs, and so on. That's multi-attribute or multi-dimensional data. And you notice that's a mixture. That's a mixture of the text and the scalar data, right? It's a mixture of different data types. So we have to, when we're talking about data and data visualization, we want to think about the dimensionality of the data, the domain that the data is in, right? Where does it come from? What are the boundaries, the starting points and the ending points? What is the top and the bottom? How is the data distributed? Its scale, how big is the data set? And how many data samples there are, right? So scale, size, and resolution. These are all factors to consider when we're trying to design some sort of visualization. And then we have to think about how it's going to be presented, right? Is there an inherent spatial domain? Like, is it scientific visualization data, or does each data sample have a special location associated with it, a special time-space point? If there is no time and space point, then what kind of space should we use to visualize the data? That's one of the big challenges. So how would you visualize a spreadsheet of cars? Anybody already know how to do that? That would be pretty amazing if you already knew how to do that. That's what we're here for, to find out how to do that. Right? And what is the space that we have for our presentation? Do we have 2 dimensions available for our presentation space? Do we have 3 dimensions? Do we have 4 dimensions? Some more advanced questions are like, where should we put our focus? So usually the data is not all of equal importance, right? So usually there's a focal point and maybe something like context. So we focus more on the things that we think are more important, and we put less focus on the things that we think are less important, right? So where is the importance, right, or the focus, right? Usually some data is more important than other, usually, not always. And that implies maybe we can leave something out. Can we leave out something? Question?
Yeah, did you about the importance here? Is that the question which you asked it in the beginning of your research?
So, for example, in the medical example, right, we have volume data. Like you put a person in a CT scanner or an MRI scanner, they're in a volume, and what you get, the output is volume data, right? It's a cube of data, and the data is not the same importance. So you get a lot of data that's just empty space. It's all the space that's surrounding the person. It's usually not important, so it's usually left out. And that's an example. So the focus in that case might be bone structure, maybe, not always. Does that answer your question?
Yeah.
And that's true about a lot of data sets. There's usually some data that's more important than. So if you're shopping for a car, what's one of the more important data aspects if you're shopping for a car?
Fuel consumption.
Fuel consumption is going to be very important. It's not the most important though, is it?
Depends on your budget.
Yeah, the price. The price. The price is probably the most important, right? And then the fuel consumption. And well, I thought you were going to say the color, actually.
Because the decision to buy a car, like usually I say color,
Okay.
or like my husband goes like, "Are you crazy?" The color is the last thing you should think about.
The color, well, the color is the most important if it's a rusty color, that's very important. You don't want to buy that car. These are just some examples. So this is some examples of one-dimensional data and one-dimensional data visualizations. The N means any kind of data. So text data or numeric data. So a singular numeric value or textual value can be mapped to a set of real numbers, one-dimensional real numbers. So in this case, a set of test scores or city miles per gallon is mapped to height. So there's just one dimension. The n in this case is city miles per gallon, and then the height is the real number, right? So this is just some examples. They're not really important. Bar charts, pie charts, histograms, bubble charts all fit into this category, right? They're examples of one-dimensional data visualizations, and these are the ones you're familiar with, right? These are the bubble charts. So the thing that's changing in the bubble chart is the radius, the size of the bubbles. So that's the one dimension that's changing. Here's a set of real numbers being mapped to height again, right? So this is numeric data only, one-dimensional numerical data being mapped to height again. And this is very, very common for time series data, right? Time versus amplitude. So time being on the x-axis and then amplitude on the y-axis, recorded over time, right? Or a graph. And this graph, by the way, is a zoomed-in view of this little spot there. Here's an example of two-dimensional data being mapped to a one-dimensional curve, right? So the data is in this two-dimensional plane, and these curves are called isocurves. So that means the value along these curves is always the same number, right? That's what isocurves are. Curves of constant scalar value. Here are some more isocurves. Does anybody know where you see isocurves on a daily basis? Maybe you didn't know that you were looking at isocurves, but you do see them if you watch TV, I guess, on a more or less daily basis. The weather report, exactly. So the weather report will show isocontours, usually of pressure or temperature. Show a line that says everything on this side of the line is warmer than everything on this side of the line, or here's a high pressure front coming. That very rarely happens in Swansea. Does anybody know what a high pressure front usually means? It usually means sunshine. These are two-dimensional data being mapped to two-dimensional visualizations. So these are two-dimensional vectors, right? Two-dimensional vectors being mapped to two-dimensional arrow glyphs, right? So the glyphs have an x component and a y component, so they have a direction. I'm lying a little bit. Does anybody know how I'm lying a little bit here? It's because these glyphs are, you could say that these glyphs are three-dimensional, and this texture is three-dimensional because there's color. So I'm mapping two-dimensional data to a three-dimensional visualization. These glyphs are two dimensions, they have a direction, two-dimensional direction, but they also have color, which is a third dimension, actually. But the idea, hopefully you get the idea. And these are some three-dimensional visualizations, right? Three-dimensional fluid flow data being mapped to three-dimensional glyphs, or streamlines in this case, or stream surfaces in this case. Right. If you were taking the full-length module, then these topics would be covered in more detail later on in the module, the flow visualization part. These are some examples of the volume visualization. So this is three-dimensional data, the volume data, being mapped to a one-dimensional surface, an isosurface. So every point on this surface has the same scalar value. It is the scalar value that corresponds to the bone. Right? It's called an isosurface. isosurface. And here's another isosurface. Anybody know what this is? Right. Anybody want to guess what that could be? Does it look familiar to anyone? No? Doesn't look familiar? Nobody wants to hazard a guess? Should I call on someone? That would be scary, wouldn't it? Oh, I see. How about James Hurd? What do you think this looks like?
It looks like a walnut.
Exactly, that's what it is. Walnut, yep. Good guess. This is an information visualization example. So this is an arbitrary number of one-dimensional data sets, the columns in a spreadsheet, for example, being mapped to real numbers of an arbitrary dimension of real numbers. So this visualization is called parallel coordinates. So there's one axis for each attribute in the data, and that each attribute is being mapped to a special position along this axis. You can think of it also as the height. And then they're being joined together by polylines. This is a high-dimensional glyph, right? This is for rugby events, actually. But each part of this glyph represents some aspect of the data. For example, like the position of this arrow represents when the game started, shortly after the start time, and how long the event lasted, right, by the thickness and so on. So that's about the data and data characteristics. We're just going to mention a few things about color before we get to the applied part, or the third part of the class. So color, you can't have visualization without color these days, right? It's not much fun without color. So color can strengthen the visualization or strengthen the information. It's another visualization channel. If you're trying to group the data into different categories, like high, low, medium, medium high, medium low, or something like this, we generally use seven or fewer colors, like 5 to 7 colors. Because if we have too many colors, then it's very difficult to interpret. It's difficult if 2 colors are too close to each other. The human visual system can definitely distinguish between more than 7 colors. Right? Are there any artists in the audience? I know my oldest brother has a degree in art, and one of the homework exercises that he had was to paint 300 different colors. Just here's some paint, make 300 different colors with them. I remember that exercise. So a person can definitely, for artistic purposes, all 300 colors is great, but for visualization purposes, we generally only use maybe 5 to 7. There's something called the rainbow color map, which is very common. We're not going to go into detail, but the rainbow color map is not linear. So if you look at that RGB color map that's used in a lot of visualizations, the green occupies more than its share of space usually. Color perception depends strongly on its context. This is a great observation. Did anybody see that thing that image that had gone viral on Facebook and Instagram of the dress, and like you saw either a yellow dress or a gray dress, I think? Blue or gold dress, right? So some people saw blue and some people saw gold. Did anybody manage to swap the colors? Like, so I could get the other color, right? So what color you see, that the key to that illusion was the context, right? Whatever color you saw depended on the context. What's the context? The surrounding colors. Or the colors you saw just before you looked at the dress. Which is really interesting, right? And I'm actually going to show an example of that. Some people are colorblind. Colors have associations. Those are pretty obvious. There's a special tool called ColorBrewer that's very good, offers very good advice when looking, if you're trying to decide, oh, I need some colors for my visualization, what should I use? We always say, check out ColorBrewer, and it will give you some recommendations. I'm only mentioning this briefly in this class. In a full-length class, I might get out the website and give a little demo of this. It's a free tool online. This is the colors depend on context, or this is all, one of the illusions is called the Mokpo Effect. So, eyes, or the visual perception generally tries to focus on boundaries and emphasize boundaries. And sometimes this can create illusions. So in this particular example, if we look at, say, the middle rectangle, and I ask the question, is the middle rectangle the same color in the whole space of the rectangle? Is it a constant color? Would you say true or false? Yes or no? Okay, who says yes? Raise your hand if you said yes. 1, 2. Anybody say no? 1, 2, 3, 4. So for some people, it looks like, if we look at this rectangle, that this side is brighter than this side, right? It looks like we're going from bright to dark, doesn't it? That's what it looks like. But actually, in reality, it's all the same color. It's a constant color. And the reason this side looks darker is because the boundary it's bounded by a brighter color here and a darker color here. Right? It's actually an illusion. You can see the illusion if you print it out and then you cover up the neighbors. But if I just cover up the neighbors like this, then you can sort of see, oh wow, it does look more constant, actually. Even though I didn't cover up the neighbors. So it's a well-known illusion. This is just a brief mention that different devices can create different colors, a different set of colors. It usually depends on how much money you paid for the device. But the range of colors that I can see on my laptop is greater than the range of colors that come out of the projector. Right? So this image is going to be slightly different than this image. Probably the time you run into that is when you try to print something out. Right? When you print something out, you notice the colors have changed, usually. So if you want to really high quality printout photo, you need to pay some more money usually. Some general guidelines. Grayscale lines are very useful for color boundaries. Avoid dark blue for details and animations. And there's a surprising number of examples where people mix red or dark red with dark blue. I see this all the time. It's a very bad and hard to see color combination. I see it all the time now, it's surprising. Avoid high color frequency. That just means too many colors in too small of a space. Right? And then the last example, we saw that the surrounding colors are important. So the surrounding colors affect the color that you see. Right? Context is important. And color is good for qualitative visualization. That means putting visualizing data in different categories. Right? And color can be used to strengthen boundaries. That's also illustrated in that 2 slides ago in the mock band effects. So the perceptual system is always trying to enhance boundaries, the visual perception system. Okay, that's the end of part 2. Again, I point out these books, the interactive data visualization book. The website is actually called idvbook.com. You can look at the website of that book. IDV. Yep. Interactive data visualization. So it's actually idvbook.com. It's a pretty cool website. And if you get a copy of that book, go to the the index and look for the Swansea images. And same with this one. If you can actually find Swansea references in all 3 of these books. That's why I put them. That's why I recommend them. Any questions about the second part of the introduction? Everybody remembers where to get the lecture slides, right? You want to look at the lecture slides. And if you want a preview into the rest of the module, you can also look at the lecture slides. So the lecture slides for the whole module are there. Okay, let's take another break then, before we start the lab, the hands-on visualization exercises.